Saxon Advanced Mathematics. Welcome, students. This is a supplemental video. We're going to revisit the topic of sinusoids, which we learned about over several different lessons. And this lesson is just going to put it all together for you once again. And then I'm going to work a couple example problems to just help you stay on board with them. All right, just kind of a rehash of the whole lovely affair that are sinusoids. I want to start by going all the way back to the beginning and looking at the very basic forms of a sinusoid, okay? Let's just start by looking at the positive sine curve. Just looking for pieces of paper to cover up the part we don't want. Okay, here's a basic sine curve, we call it, right? It's the sine function. And we notice that it starts, here's the y-axis, here's the x-axis. We have it divided off into 90-degree sections, just like the quadrants on our circle graphs. It goes down into the negative numbers and up into the positive numbers. This row is between 1 at the top and -1 at the bottom. This is called the center line. And the difference from the center line to the top and the low values are called the amplitude. We see it has a center line of 0, because it's halfway in between 1 and -1. And we see that it has an amplitude of 1. It just goes up that high, and then it goes down the same amount. Okay, that's cool. Notice that with the positive sine curve, it's coming up. The line is crossing the x-axis and climbing to its high peak as it crosses here at the y, right? It's 0 and it goes up and then it goes down all the way to the bottom and then back up to the baseline where it started. And we notice that from here to here, it's 360 degrees. That's called the period of the sinusoid, okay? That's how far it takes it to go from the beginning to the end. Or another way to put it is it reaches the same point. It's always crossing that x-axis and going up again, 360 units out. And we could continue to draw it, chunks of 360, and it would always get one full wave in within 360 degrees. These are degrees, by the way. All right. Sometimes we call the curve x. Sometimes we call it theta. Doesn't matter. Sometimes we measure it in degrees. Sometimes we measure it in radians. All you have to do is remember that pi radians equals 180 degrees, and you can translate back and forth. So that doesn't change it. That just makes it look different. All right. Now, what we can do is we can also have a negative sinusoid or sine curve. And here's what that looks like. Now notice the center line's the same. The amplitude is the same. But this time, instead of going up as it crosses the y-axis, it's going down. And then it goes all the way to the bottom, back up to the middle, up to the top, and then it starts its roller coaster. Oh wait, sorry, it should come down more. To there, right? So this one is a lot the same. It's just kind of like it got flipped over, right? But it's going down at 0, and then it's going down again at 360. So we see that its period, the full wave, is 360 degrees again. Okay, that's nice and normal. All of these things are normal. It's just what we think of. Again, we used x instead of theta, and we used degrees instead of radians, okay? That's the sine curve. He always is the guy coming up. This is what you want to memorize, right? Sine is coming up and it's at 0. It's crossing the line and going to its high point. Minus sine point is going down, right? It's the opposite. Okay, now we're going to look at the cosine curve. Now the graph is set up exactly the same. We have a center line of 0. It goes up 1 and down 1. We're marking off in 90-degree increments, but our curve is behaving differently. What it's doing is here at 0 on the x-axis where we're crossing the y-axis, it's at a peak value. Then it goes to the midline, then it goes all the way down, back to the midline, and back up again. oh, the sine was coming up here. This one is at the top and it's going down. So the curve has kind of the same shape, but it starts at a different place if we measure this as the starting place. It still completes its full transit in 360 degrees, right? It starts at the top, goes all the way down, and then comes all the way back up at 360, and then it's starting its trip again, okay? And then we have a negative cosine curve, and just like the sine curve, it behaves as the opposite of its partner. Regular cosine starts at the top, negative cosine starts at the bottom. It goes all the way up and then comes back down, again completing its full transit in 360 degrees. Okay, so that's pretty cool. So we definitely need to start by understanding these four functions and having a really good understanding of how they work, because we're going to take this much and then we're going to make it more complicated. All right, so this is the starting point. That's why we did this as a review problem back in December 11th, because I knew we were going to be building on this, okay? So now what we're going to do is take a look at how we can take these basic functions and make them more complicated. There are 4 different variables that we can play with. And I've written... Here's our original function, y equals the sine of x, right? That's how it looked here. So that's where you see that original function here. Obviously, we can take the cosine or the negative sine or the negative cosine, just like we did here, and we can write equations based on those with the a, b, c, and d, but we're just going to look at the A and the B and the C and the D. We're going to focus on that, and whether it's sine or cosine doesn't really matter, positive or negative. All right, A is the value of the center line. Normally, it's at 0, okay? So let's call the default is 0, right? That's how we had it here, where they were going through at 0, right in between 1 and -1. But we can change that up if we want. That's really easy. We can put different values in there. B is what we call the amplitude. And that, the default is 1. Because as we saw here, it's going up to, its high point is at +1, its low point is at -1. So it's just straying 1 unit up or 1 unit down. So we call that the amplitude. All right. C, letter C, is called, I'm going to go down here, is called the period coefficient. And what that shows us is whether this curve completes its full circuit in 360 degrees, or is it squished? Does it complete it in a shorter number of degrees, or is it stretched out? Does it complete it in a higher number of degrees, right? It doesn't have to complete it within 360. We could have a really fast one that got all the way done in 180, or we could have one that needed 720 degrees, okay? So we can squish that curve or pull it apart, stretch it, and make it softer, the curve softer. And that amount of tightness in the curves of the sinusoid is called the period, okay? And the way we calculate that is we take 360 degrees and then we put the period of our curve. And we're going to work examples on all of this, so it'll make a little bit more sense. This one we have to calculate. Okay? So that one's a little bit different. This is called the phase shift. And most students think this is the trickiest one to figure out. What the phase shift is all about is, this is my glue hardened yarn one. You know how you take Elmer's glue and squirt it on something and then let it dry? Pretend that we did that to that curve. It's not attached to the page, but it's rigid now. We can pick this curve up and shift it over to the right or over to the left and put it down in a different place. It's still a sine curve, but it's not on the graph exactly where it belongs. So we say that we have shifted the phase. It's not about stretching the curves, it's about moving where it's beginning and ending, okay? That's called a phase shift, and that's really hard to describe unless we have an example. So we'll get into that in just a minute. All right, so these are the 4 different ways that we can vary a sinusoid. Starting from those basic 4 that I've been showing you, we can mix it up. Now I need to find my problem. Here it is. Write the equations of these problems as a cosine function. Now remember, this can be sine or cosine. It doesn't matter. This word just tells us what to compare it to in our original diagrams. So let me draw for you this picture. Here is our y-axis, and here is our x. This is the way we mark those on these. Sometimes this is theta. You just put a theta there instead. It's exactly the same. All right. The mark up here is 5. The mark down here is minus 11. That's weird, right? Now, the units on our picture look a little weird. They don't line up quite right, do they? The way they did on our examples. Look how it's kind of staggered and weird. Okay, and we see there's a high point here. This is 180 degrees. I'm copying all this straight out of the book. That's at 180. Then down here, when we hit the low point, that is 900. It crosses over halfway in between, but there's no number there. And then out here, it rises to the top, and that is 1620 is where it hits. So it crosses again there, but there's no number there. And I'm just double checking my numbers. Yep, that's right. Okay, then here's the high point. It comes down here, but its low point is at this marker, and that says minus 540. And then it comes back up, and its high point is here at minus 1250, 60. Okay, so what is this crazy curve doing, right? It looks weird, but we can figure it out. It's going like this, and then it's going down, and then up. Okay, and we're told, by the way, this is problem, this is the odd number. So this is one of your homework problems. I may be helping you out. Okay, so what this, and we're supposed to write this as a cosine curve. Okay, cosine, as we remember, starts high and then comes down. So we're going to consider this to be the start of our function. All right, we can see there's a lot going on in this curve. It's crazy, but let's start with the easy part. Let's start with the center line. Okay, so I'm going to write y equals, because that's always the same. What's our center line? We have to figure that out. It goes from minus 11 to 5. That means there's a range here of 16 points, right? 5 to 0 is 5, and then minus 11 is 11 more, so that's 16 total. So that means that this distance must be 8 and this distance must be 8. So this would have to be -3 at the center line, right? Because then you'd go up 8 to get to 5 and you'd go down 8 to get to -11. So our center line is -3. Plus, what's our amplitude? The amplitude is the measure from here to here. Oh, well, we already figured that out, right? It's 8. Okay, times, we put cosine, we put the name of the function there. Now this is our period coefficient. So to figure this out, we have to find out how many degrees it takes to repeat the full cycle from here to here. And I'm going to switch to doing my calculations in my little book so that you can see, but I don't have to turn away from my picture. Just looking for a blank page. Here we go. Okay, so our period starts at 180 and it ends here at 1620. So we subtract to find out how many degrees it takes to go from beginning to end. (1,440 degrees equals our period, right, of our graph here. That's from one starting point to another starting point. You can measure it if you want from a low point or the crossing point. And look, that works out really well because if we do it at the low point, it's -540 and +900. So we would add those and look, we get 1440 again. The tricky thing about measuring the period is we have to work with the numbers John gives us, and he doesn't always fill in every little detail. So like if we wanted to go from where it goes down across the line, we don't have that number. So we have to find a point that we can work with. So now we've found that there are 1,440 degrees in our period, not 360. It's super stretched out, right? Now, how do we calculate the number that we put right there? Oh yeah, we take 360 over the period of our curve. So the coefficient, the number that we actually put in the equation, equals 360 over 1440. Now, what do you want to bet that 360 goes evenly into 1440? It should. John's not going to be that mean. Here's what my brain's doing. 2 times 360 equals 720. That's easy. 720 plus 720 gives me 1440. So that tells me that 4 times 360 must equal 1440. So this reduces to 1/4. So this is the coefficient that we're going to put right here. Now we can set up our parentheses and we can say x. Now before I put the sign in, I want to stop and think. This is our phase shift. So what we do is we look at where we normally think of our cosine curve starting. Cosine normally starts at the top and then goes down. So where is our curve doing that? Where's the closest place to the y-axis where our curve is starting and then going down? It's right here. Okay, that's 180 degrees, John tells us by this graph. So what that tells me is that somebody picked up our Elmer's glue dried yarn and moved it to the right 180 degrees before they put it back down. So our phase shift is 180 degrees and the minus sign belongs in there. So if it says minus 180, that means it was a positive 180 shift, right? Because the sign is automatically a negative. We've seen that in other equations. It's a little head trippy, but a minus sign there means we go to the positive 180. So this, let me double check and make sure that's right, 7115. Yes, that's our final answer. okay? So just go one at a time. Start, I mean, A and B are the easy ones, so stay with them. And then this we calculate based on matching points. We find out how many degrees that is and make the little fraction. And then the phase shift, we just have to look carefully. Where is it actually closest to 0? Sometimes the closest point will be over here. So sometimes we'll have a positive phase shift, and that's confusing. But what we do is we look for the place where it normally starts that is closest to the y-axis. So that's why I chose this one and not this one, or even that one, right? I pick the normal starting point that is closest to the y. All right, let's do one more. And this is going to be also from the homework of 71, but this is going to be problem 16, and this one's going to be in radians. And that's why I like it. The radians aren't harder, they just make our head work a little differently. All right. Well, here my high point is 3, and my low point is -1. Okay? Grace is going to bark for us. Okay, so the high point is at -π/2. Then it crosses. Then I have a low point, which is at -5π/2. And then it comes up. Grace is having some really cute puppy dreams. And my next high point is -9π/2. Okay, I'm just talking as I draw the picture. Sorry if that's distracting. Okay, over here, I'm coming down. I cross, but I go all the way down here. Can you hear her? And then back up. And here's my high point. And that is at 7π/2. Okay, so let me make sure I have all my dots in the right place. This is a dot. This is a dot. Okay. Once you get your dots in, then the fun happens because you get to draw it. Okay. We're trying to draw a cosine curve, so it's going to follow this pattern. Y equals A plus B times the cosine C, and this one is also x, so I'll use that x minus D. Okay, that's naturally a minus sign. A is the center line. So we look at this, our high point is 3, our low point is 1. That means our total range here is 4 points. So that means this must be 2, and this must be 2. So our center point here must be +1. So our center line is 1, and our amplitude is 2. Cosine I copy. Here, let me copy this part too. Now we need our period coefficient. Okay, so I'm going to measure from this, because this is the closest starting point to the y-axis. Cosine starts at the top and goes down, right? Cosine's the roller coaster, where you just jump in at the beginning. They're both roller coasters, but with cosine, you start at the top and you just go for it, right? And then here's the next time that we repeat the cycle. So that means our period equals, and if you take this one and subtract this one, it will be a great way to calculate that. So 7π/2 minus π/2 turns out to be 4π, right? Because this becomes a plus. 7π plus π gives me 8π/2, and that's 4π. Are you with me? Okay, so that's the period. Now for the coefficient, I don't think I wrote this in our notes. Let me go back and have you add that to your notes. Here, when we're calculating our period of coefficient, it's 360 over the period of our curve, or if you're working in radians, 2 pi, because 2 pi, pi equals 180, right? So that would be 2 times 180, 360. Period. This part's the same. Okay, so now we're here. We want to calculate the coefficient using radians, so we use 2 pi on the top, and then we put our period on the bottom. So our coefficient is 1/2. So I put the 1/2 right there. X. Now I have to calculate the phase shift. Now, our phase shift is a negative shift this time, right? Which means I'm going to have a negative value that I put in, which means when I combine it with this, it's going to go positive. And the amount it shifts is pi over 2. We're working in radians, so I get to use it exactly as it is. So we shift it to the negative pi over 2 units, but that becomes a plus because the formula has a minus in it. Okay, so this is our answer. Let me just double check. 1 plus 2 times the cosine of 1/2 quantity times x plus pi over 2. Yay! All right, I hope this helps you. Let me know how these are going. I hope you get the hang of them because they're really kind of super fun. Once you get all the details flowing, it feels very satisfying to write the treasure map. Okay, that's all. Goodbye.